will be better next time I try. And even if I still can't do it, yeah, you know that I'm gonna stick to it. Yes, it's all about going through it, and I'm gonna tell you why. Whoopsie, whoopsies, I made a mistake and it's okay. It's okay. Whoopsies are what it takes to get better and better every day. Whoopsies, I made a mistake and it's okay. It's okay. Whoopsies, help me look, see, I'm better at this today. Woo! Whoopsie, 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 whoopsies.
I'm a little embarrassed when I look at my drawing compared to this. I'm just not getting anywhere with this. It makes me wanna hide. Aw, don't be embarrassed. Don't hide.
You should have seen mine the first time I tried. It took a lot of whoopsies to look this way.
No one's perfect on their first day. Whoopsie.
Whoopsies, I made a mistake and it's okay.
It's okay. Whoopsies are what it takes to get better and better every day. Whoopsie, 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 whoopsies.
Well, what about this? I want to jump rope, but nope, I just can't do it.
Well, not yet. Come on and practice with me. You'll see there's nothing to it.
Whoa! Whoopsie.
Whoopsies, I made a mistake and it's okay. It's okay. Whoopsies, help me look, see, I'm better at this today. Woo!
It was only a dream, the waves of evil crashing over us. It was only a weak and faithful scream beneath the battlements. I know it's hard to follow before it's too late. Wake up, my love, please don't give up on me. It's hard. Wake up. It was only a dream, the waves of evil crashing over us. It was only a weak and faithful scream beneath the battlements. But I know it's hard to follow before it's too dark. Wake up, my love, please don't give up on me.
What is up? What is up, you guys? We are back at it again. Another 100 days of Rootkit. Today marks 25% completion. 1/4 of the way through. You guys are doing it. You guys are cranking through this. Oh my. We've gotten very, very far. Very impressive. Very impressive. I'm impressed for all of you guys who've stuck through so far and have stayed in and learned everything. It's been extremely impressive and motivating for even me, alright? Let's switch this over here to our more chill, casual music. Now, if you're returning, well, thank you. If you are new, well, thank you for joining us. Let us give you the basic rundown, alright, shall we? We are Rootkit, a non-profit here in the US of A. We are 100% tax deductible, registered. You can go look us up. We are also Platinum Transparency. We are a very transparent org and pride ourselves on that. So if you have any questions, just ask them and we will be more than happy to answer them. We are doing free giveaways. We are on week 4 right now. You have 2 days left to participate. So if you go over to our site, click on blog, you'll see the week 4 giveaway. You can enter here, just basic things like subscribing will get you points, and then you can potentially win the giveaway. We're going to be drawing this on Sunday. Now, if you like what you're doing and you want to help support us, then you can go over to this link, which I will drop into the chat because it's always messed up on the videos. Let me find the chat here. Bam. And bam. You can donate to us, and then, what was I going to say? You can donate to us if you feel inclined, if you have some extra dollaroons, and you like what we're doing here. Depending on the tier that you donate at, you'll get various different merchandise, alright? Including all the way up to this amazing, amazing sweater I have here. Now make sure you stay tuned because we may be giving another sweater away. We've already given one away, and most likely we're going to be giving some more away, but stay tuned for that, alright? While we're donating, all donations are being matched 1-for-1 up to 10,000 by an anonymous donor. So every donation you make is going to be every dollar you donate will actually be $2. All right, super awesome. We have some goals here like teaching for 24 hours straight, shaving my head here live on stream, and the one we will not get to, I don't approve it. All right, but that's shaving my beard. No one wants to see that. All right, no one wants to see that. So if you want to follow along, if you go over to our GitHub, you can go to our org's page, and there you'll see the CompSci roadmap. You can follow along here. Today we start operating systems. We are out of the cruel, cruel world of networking and protocols, and now we enter OS land. Much more fun, much more entertaining. Sweet, sweet, sweet. Any questions, comments, concerns that anyone has before we start? See, a lot of people are chatting, saying hi. We're out of time. Ask this: when does the exam will be after this study? So the exams are whenever you schedule them. They can be at any time. We are not doing the exams here on stream. We're not facilitating exams here on stream. We're purely just teaching people here on stream. All right. Are you guys ready to dive into operating systems? Coffee. I love me some coffee. All right. So we talked about it before. If you can set up Docker, that will help. That will be great, especially when we move further on. If you can't, that's okay. You'll just need to memorize these like flashcards. You don't actually have to have time on hands-on keyboard in order to pass the exam for some of these items. So let's move on and talk about operating systems, shall we? Windows. Windows is one that you should be familiar with. I would be kind of concerned if you weren't familiar with it. It is the biggest operating system. It's just about everywhere, pre-installed on most computers everywhere in the world, and arguably runs the consumer realm of the world. Not the server space of the world, but the consumer level. So normal computers that a consumer would use, or work computers that a worker at work would use. But before we continue forward, we should kind of answer the question in general, like, what is an operating system? What's the whole point of it? Well, if you remember back when we talked about hardware, hardware is just kind of there. It kind of just does stuff automatically as electricity goes through it. Hardware, anything that can be done on hardware can be done on software, and vice versa. They are pretty interchangeable. The only thing is, if you want to make it hardware, you physically have to make something. All right, software is superior in a lot of cases because you can dynamically change it as needed. So the thing though is, software just doesn't automatically work. If you grab something like a CPU and some memory, and then throw them on a motherboard and then plug in a hard drive, nothing will happen, because you have no operating system by default. You have to install it. It's the job of the operating system to then connect these, because they'll be there, they'll exist, but they won't talk to each other like how we're used to. Nothing is automatic. We take it all for granted because we use operating systems. The operating system's job is to orchestrate, all right, orchestrate all of the hardware underlying all the software that you're using. It will orchestrate it, it manages it, it makes your memory work, because by default, memory is, you can kind of think of it like an empty building. It's a lot of space. There might be a bathroom or two, you know, there's some useful things in there, but it's empty. There's blank. It has no meaning or purpose. It's you developing the operating system, your job to go in there and become like an interior designer, essentially. Say where everything will go, where the light fixtures go, where is the HR department going to sit, where is like the manufacturing area for, I don't know, maybe your 3D printing robots or something. Where does that go? The operating system will dictate that. The CPU, by default, is just something that sits there, has a bunch of pins underneath it, and if you run electricity on those pins, it will perform a certain action. It's basically like a bunch of levers. But it doesn't actually know anything. It doesn't do anything by default. An operating system will then orchestrate those levers being pulled along with your memory, this nice warehouse you have, and where things will live and how things are moved around. All right, the operating system does a lot under the hood for you, and then it builds on top of that and builds on top of that until you get what you know today as an operating system. Now, back in was it the 80s, early days of computing, there were a lot of operating systems out there. All right, every individual company was making their own operating system. It was the wild, wild west. You see this pattern all the time in tech, where something new will come along. There will be 300 companies that are trying to get in on the action, and then after 5-10 years, there's only a couple people left. Some people are saying right now that's what's going to happen to all of the streaming platforms. Everyone has their own streaming platform, but they're guessing in a couple of years from now, they're going to start consolidating, and there will only be a handful of them, because it's really inconvenient for the end consumer to have to juggle around or know what works on what if there's 10 different operating systems. Because you might know, if you have a Mac and a Windows computer, you can't just use programs between them. There are compatibility issues, and you run into this a lot because the operating system, again, is like an interior designer or an orchestrator. All right, they do whatever they want or how they see it fit. They don't need to follow any rules. There's no guidelines. It's totally up to you. That's the reoccurring theme in all of this that we've been mentioning over and over again. Data, at the end of the day, is arbitrary. It's just ones and zeros. It's on how you want to interpret it. All right, we got two operating systems that really won out. That would be Windows, all right, and then Unix. Unix if I recall correctly, was a closed source operating system just like Windows. So closed source is going to mean that all of the code that's been developed to make the operating system is hidden. All right, it's private. So Microsoft does not openly share that. It is private behind walls, and you're not allowed to see it. Open source, on the other hand, means that you can view it, you can look through everything, there's no hiding, and you can actually go even further than that. You can contribute. If you see maybe a bug or an error, or you want to add in a feature, you can then go about adding that feature and then submit it, which is really, really cool. So Unix, I believe, was completely closed source, and it was made at Bell Labs. All right, you'll see them a lot on the early days of computing. And so from that, yeah, proprietary software. So it was proprietary, but a lot of people really liked it. So Linux was made. Linux was a clone of Unix. All right, it was a clone of the operating system, but it was made to be fully open source and free for anyone to use and build upon. So Windows won out because they did great for their marketing, teamed up with a lot of people, and delivered on the personal computer. Mac OS won out. There was many different iterations of the Mac OS over the years, but they won out because they were the first ones. Apple was the first one to make the personal computer, right? They were the first. And Mac OS is based on Unix. It uses Linux under the hood, all right? So Linux is a broad term for just the kernel, which is the soul, per se, of the operating system. When someone says Linux, they're referring to potentially hundreds of different operating systems that are using the same soul, per se. It's the kernel. So if you look at Linux over the years, I think there is a good picture here. Let me see. Are there any questions? If you guys have questions, you can go ahead and just drop them in the chat, and I'll be looking over and answering them periodically. We got our class, live stream, thanks for joined. We go, awesome. Glad to have all of you guys here. Let me go to Linux. Oh no, I'm blanking on the term. Linux distributions tree. Here we go. So you can see from some of these graphics. Oh, this is the one I wanted. Yeah, see, this one's on Wikipedia. I don't know why this one didn't come up. That isn't. I don't want to save it. What? But why? Why are you so small? All right, hold on. Let me click on this. Here we go. This is what I want. There we go. So this is the distribution map of Linux. And as you can see, there's been quite a few different Linux operating systems that have came out over the days. The best thing, though, out of all this is it is still using the Linux kernel. So they all are compatible with each other to a certain degree. So if you were to write some software, it should work to a certain degree on all of these operating systems, which was new and revolutionary at the time. It's something we take for granted all the time nowadays, but it was through all of the chaos here where things became more established. Now on this chart somewhere, you will actually see Mac OS. It is based off of FreeBSD, I believe, if memory serves me correct. All right, we're not going to keep going through this anymore. It should be further back. This is only to 1992, unless is that when they switched. If we look up Mac OS, we can look at the Wikipedia page and see right here that it is Unix-based operating system, and right here somewhere it should say, are you really gonna make me look for this? Why do you gotta do this to me? Make me look like a fool. Unix. There we go. BSD it should be FreeBSD. Someone went in here and changed this article, I'm telling you, all right? But it is based off Unix. So it is in the same class as Linux operating systems. It's diverged quite far. So some people won't really classify it as Linux because it's not using the same kernel. They've actually went and built their own, but they do share a lot of similarities. So it's not uncommon for you to be able to make a Linux application and it works immediately on Mac OS, because they're all based off of the Unix concept and how Unix handles everything at the kernel level. All right. So in extension, Android phones are Linux based, and iPhones are going to be the also Linux based. They're going to be based off of the divergent kernel that Mac made, but they are all based off the same kernel. They utilize, at least used to utilize, I don't know if it's still the case anymore, but the same kernel that Mac OS uses. So it's really neat, and most exploits that work on Linux will typically also work on Mac OS. They used to have I don't know if this is a shocker for you guys, but Mac used to have a massive ad campaign about how it never got viruses. It was a big viral campaign. They were quite clever, quite funny, but the thing is, there were lots of viruses for Mac OS, all right? There are still lots of exploits for Mac OS and iPhones out there. You got to think of it this way, because we talked about it a little bit when we talked about exploits yesterday. It's about monetary gains for most hackers, all right? It's about how much money you can make. Windows ran the world. It was like 90% plus people had Windows computers. If I was a hacker, why would I want to spend my time going after Mac OS individuals when I could make a Windows exploit and just use it on way more people? All right, my chances of winning the hacking lottery are way higher on Windows than it is on Mac OS. But now you'll see more and more public exploits of Mac OS out there, because they've grown in market share quite considerably and have actually, I think, still continued growing in market share. Mac OS market share. Do I got an overtime? This one's overtime, right? OS X. This is only for what, a year? I thought it was more. I thought they hit double digits. Maybe it was iOS. But they've been growing their market share. It must be in the iOS realm. Or maybe I'm just lost in the sauce. This is only a year. I wish there was more here. But you've been seeing, there has been more and more coming out of lately. Any questions so far? So again, a recap. Operating systems are what do all of the orchestration and let you actually communicate with the hardware. All right, so you can actually have some meaningful interaction going on with all of these wires and cables in front of you. There are several different types of operating systems. If you really want to break it down, there's only really like two. All right, that would be Windows and Unix-like operating systems. You'll hear them usually referred to Unix-like because they are not Unix. They're just based on Unix. So that would be Linux and Mac OS. Let's see here. So there's some core concepts we need to talk about and get our vocabulary down when we're talking about operating systems. There are users. Users can be anyone that is using the application, the computer, whatever it is, they're logged in and they have a current session. You know, when you make a new account on a computer, that is going to be a new user on there. Potentially, you could be mimicking a user. So, for example, if you're connecting to a web server, you're at that time mimicking the web server user or whatever user is created for the web server, and your permissions are limited to whatever that web server's permissions are. At any time you're interacting with a computer, you have been granted a user profile. That may be a guest, an actual one that you created, or a user account that was made to run some type of application. While I'm using this word application a lot, you might be more familiar with it as the term app. App is just short for application. Application is anything you can install and run on your computer. Typically, application doesn't have to mean it, but most people will use the word application in association with something that has a interface, a graphical interface, so something you can visually see. And they'll usually use other terms to describe something that is going to be command line based, like a program, but they could all be given the term application. Let's see what Google says exactly for the term application. An application program is a computer program designed to carry out a specific task other than one relating to the operation of the computer itself. So, in other words, pretty much all software as you know it. It's, again, some people will say they have rules put into place to separate things like the word program, application, and software, but they're also used pretty interchangeably. So don't worry if I use them interchangeably or if you use them interchangeably, no one's going to get mad at you. They're used pretty commonly interchangeably. Kernel, on the other hand, refers to the heart and soul of your computer. It is the orchestrator of your computer. It's what manages and makes the blank halls of a warehouse decorative and work. It's what puts order to the chaos. It's what sets rules and says there will be users and there will be admins and where things load into memory and how the CPU works and who can talk to the CPU at any given time. All right, it does a lot of management. It is a very important piece of your operating system. If anything bad happens to your kernel, lots of bad things can happen to your operating system. It's the equivalent of your heart, all right? If something bad happens to your heart, it's not good for you, all right? You might have to take medications, or you might have, I don't know, the occasional heart attack or two. Not all the time will you die. Sometimes you'll still be alive, but you might be in a painful or weak state. Same thing with your kernel. Your kernel, it could be destroyed and your computer is dead, or it may just be in a weakened, crappy state, all right? Kernel is important. Again, it does all of the orchestration. It figures out what goes where and how it goes and how you interact. Be nice to your kernel, all right? Don't get it mad. Don't get it mad. It'd be a mistake. So graphical user interface. For now on, I'm just going to be calling things by the term GUI, all right? Because that's what they're called and that's what I like most. GUI. That's what the acronym for this is. GUI, all right? Graphical user interface. What does that mean? Exactly what it says. Graphical means there's graphics, pretty pictures. User, it's meant for the user. An interface, it's something you can interface with, play with, interact with. It is everything that you see on your screen that has pretty pictures, all right? Google Chrome, everything on this website, the desktop, all of the icons on the desktop, all the icons down here, all of this stuff. These are all GUIs, all right? These are all graphical user interfaces. This is the thing that I've talked about before. Takes a lot of time, all right? Developers don't want to spend and waste their time making these things for a lot of pieces of software. So as you'll see us moving forward, we're not going to be messing with GUIs very often. All right, the movies are all tell you lies because they think that you're immediately a hacker if you're using a terminal. No, that's just how you go about using a computer in user or in programming world, because we don't have time to make pretty pictures for stuff. That's a luxury feature. Everyone likes the luxury features, don't get me wrong, but you won't see them as common as we move forward, all right? And it's something you'll have to get used to. It's also a little more simplistic in a lot of ways because you don't need to remember where these buttons are. It takes less time to do more powerful actions. So what is that called when we don't have the graphical interface, when we just have that typewriter? That's going to be your command line interface, your CLI. So PowerShell, Windows Terminal, command prompt, a Linux shell, all right? Those are all going to be command line interfaces. It's where all you see is this command line. This is called a command line because you usher in commands to your operating system, and it will it will respond back. So we talked about ipconfig. This is a command I'm giving the operating system, and it's going to return back. This is software. This is an application that's built in to your operating system that you can interact with, that lots of pieces of software on your computer interact with automatically behind the scenes, and you don't even notice. All right, so let's see here. So again, GUI pictures, command line interface is going to be this stuff, the stuff that is not user friendly. So CLI and GUI, CLI and GUI. I'm going to be referring to them more and more as these names, as their acronyms. All right, software. The definition of software is going to be the programs and other operating information used by a computer. So software is all inclusive, where applications are technically limited in their definition to anything that's not like the core operating system. What was the exact thing it said again? Let's look at that. Specific tasks other than relating to the operation of the computer itself. All right, software is everything. So when you talk about the kernel, that would be software. Kernel is technically not going to be an application. All right, it's going to be software because kernel is operating everything. It is the orchestrator. Hardware, we've talked about this before. That's going to be everything physical you can touch. All right. If you can't touch it, it's software. If you can touch it, it's hardware. All right, here we go. So we have a couple concepts here, and this might look familiar to you guys when you guys went over hardware with Taylor. So let's talk about single tasking. So single tasking is something that all of us are very familiar with. That's going to be you committing yourself to one single task. All right, you're doing one single thing at a time, and that's all you can do. You can occasionally stop that task and switch to another task and do that task, but you only do at one single time one thing. All right, all humans are this way. All humans are single tasking individuals. It's technically impossible for you to really multitask in the sense of how like a computer will, because you have to do these things called context switching, where you can do it very fast, where you're like doing this thing and then you're doing something else, or maybe you're talking to someone and then you're also typing something. You can do it very fast, but just because you switch very fast between things does not make you a multitasker. All right, computers can and are capable of true multitasking though, which is at the exact same time doing multiple things. I guess I shouldn't say it exactly for humans, because I mean technically you can like vacuum and talk at the same time. Like you can just move your hand like this. So technically you can do multitasking to a certain degree, but computers can like really take it to the next level. They can do lots and lots of things at the exact same time. How much? Well, it depends. How many cores do you have? So technically it's all based off your core count on your computer. So if you right click and click on your task manager, if you're in Windows, this is going to vary on your operating system. You can go here and click on your CPU, and is it this one? Don't want that. Hold on one second. Pull it up. Where is it? Here we go. No, not summary view. Oh, no, show graphs. Where did this go? There we go. If you right click and you go to change graph to logical processors, you'll see all the processors on your computer. Now, this is half of a lie because, again, we talked about RISC and CISC-based hardware. RISC-based hardware is typically commonly found in things like ARM-based silicon. So that would be found most commonly in devices like your cell phone. Those are going to be the reduced instruction reduced instruction compute something on. Let me look it up. RISC, reduced instruction set computer, right? You have a reduced instruction set that's available to you. It's not as smart as a normal chip. It's very limited in what it can do. All right. In those, it can only truly do one single thing at a time per core. All right. But now we're going to be, most of us, I'm going to guess, if we're on computers, laptops, if you're not on Mac OS, most likely you're going to have CISC-based computers, which are capable of doing lots of tasks and a lot more complicated tasks at any given time. And we talked about this concept of hyper-threading. That's where when you have a 64-bit instruction, if the single instruction that you're giving the computer, like add two numbers together, is not going to take up all 64 of those bits, you can actually pack some extra information at the end. That's why you'll see typically twice as many graphs here than normal, or it will be listed here as logical processors. In reality, there are only 8 cores, and you can see, at least here on my computer, it says 8 cores. Yours may have a different account, but the logical processors will usually be twice as much, because it's not because there is twice as much, it's just capable of smartly packing data really tight to basically give the illusion that you have twice as much cores. But that will show you how much multitasking your computer can do. So worst case scenario, my computer is capable of doing 8 different things perfectly at the exact same time. And when the data isn't large enough to fill up that 64-bit instruction, we can do technically up to twice as much, 16 things at the exact same time. Now, cycles are really, really fast, so you're doing, what, millions of cycles every second, more than millions, I forget the number right now, very, very big amount of cycles every minute, or every second. So it seems almost as everything is happening at the exact same time. We have the luxury with our modern computers for it to seem like that, but in reality, not too long ago, if some of you are out there that are a little older, about 15, 20 years ago, it was pretty common to only have a single core computer. And with that came all the great frustrations of you pretty much could only do one thing on your computer at a time. You could only play a game. You could only really have the browser open. If you try to do multiple things at the same time, your computer would pretty much freeze to a halt. But now that it's very common to have multi-core CPUs, you can get away with doing multiple things at the same time. So single tasking, multitasking, all right? Single user and multi-user. Any questions so far before we move forward? Oh no, I closed YouTube again. Let me open you guys back up here. There we go. So single user, let us define single user. So single user, also known as single user mode, in which a multi-user computer operating system boots into a single super user. So what you're doing right now. So Windows out of the box is going to be in single user mode, which means only one user can be on the computer at any given time. All right, you can only have one person using a Windows computer at any single time. For those of you that might want to be a little more clever and know about RDP and set up RDP on your computer and try to remote into your computer, you'll notice you don't get a new session. It's only one user account that is live at any given single time. All right. This is the default behavior for non-server based computers in Windows. Now, Linux computers typically out of the box will allow for multi-user input. So again, single user is going to be one user on the computer working, all right, at a single time. Multi-user is going to be multiple users at the exact same time working on the computer. This is talking about software, but most server hardware will allow for this. So if you ever had to remote in or remote to a box and you got a operating system when you remote in, that will be a multi-user setup. All right. Any questions on that? Pretty self-explanatory. Let us talk about distributed. So distributed computing. So just like the word says, it's going to be distributed. So most modern servers, cloud infrastructure, stuff like that is going to be distributed computing, or it will allow for some type of distributed operating system where things are sharded, not shattered, all right, sharded. There's shards. So you're basically breaking things up and you're having pieces of it scattered all over the place, and they work together and orchestrate with each other in order to perform some type of action. Also, this can be done with software on top of your operating system, like software, for example, I don't know, like Kubernetes, where a user will access a web server, but that web server potentially has hundreds of them working underneath, all right? And it will route you intelligently to one of those servers. It's distributed computing. You have lots of computers that are contributing to one single task. Supercomputers would also be good for this example. And then again, bringing up blockchain tech, that would be distributed computing. Any questions? Let me see here. All right, let's talk about templating. I think I need to put some operating system at the end of this because we're getting other stuff here. Is this going to bring it up? Because yeah, I thought there was a Wikipedia article with all of them on. It would be easier for us to talk about them that way. Let me see what this one says. All right, we'll just go through what this one says right here. We're going to ignore the other ones and only worry about the distributed templating and embedded, which this only has distributing. I talked about templating. What is going on here? Okay, well, we're just gonna go off this because everything else is breaking right now. We're breaking the internet. Templating operating system is an operating system that allows a user to create a custom environment on the same basis with the same source code. All right, so this is going to be, you can make an actual template or a pre-configuration of the operating system and then distribute it. So for example, if you're working in IT or something, you may want to by default have it so all of the users have maybe Microsoft Words, like the whole, sorry, not Microsoft Word, but the whole Microsoft suite pre-installed. Maybe you want Chrome installed. Maybe you work at Riot Games, so you want all of them to have League of Legends, Valorant, etc. pre-installed on the computers. So you make a templated operating system based off a template that is then spun up and generated. This is a concept that's also carried over to containers. So for example, Docker, when we were using Docker, we were using templated, this is kind of a stretch, but we were using templated containers that had web servers and an operating system and stuff already pre-built inside of it. And then we have embedded. So an embedded operating system is going to be a, oh gosh, I hate this site. Why Google? Why do you have to do this to me? So it's going to be an operating system for embedded computer systems. So what is an embedded computer system? Let us bring this up. It's pretty much going to be anything that's just going to be like kind of left on its chip form. I think microcontrollers, yes, microcontrollers are in the same category. So it's a very small, lightweight, low functioning operating system that's meant to do just help you with orchestration of the bare minimum things, like I guess turn on lights, or it's not really a good example, but I guess a better example would be stuff like the firewalls, for example. We talked about firewalls yesterday and how they're more and more, it's more and more common to have full operating systems on them with software, or just straight up use a normal computer with software. But previously they were mostly just hardware based. Embedded operating systems, which is a really like bare bones thing that allows you to do just basic functional changes to what is going on. For example, a firewall, you would want all traffic blocked except for maybe certain types. So the operating system would just allow you to change it. Would all its existence is allowing you just to change a couple things here and there. But it's pretty bare bones and is not like how you think an operating system is today. Any questions on that? Yeah, I guess Internet of Things devices would be incorporated in this. So things like your oh my, I can't talk today. Your smart speaker, your cameras, for your like surveillance systems, your smartwatch, those would be teetering on the embedded system. Depends, because some of them are made with Linux built into them, but a good amount of them are using an embedded operating system, which is more bare bones than normal. Load balancing. Load balancing kind of goes into distributed. All right, load balancing is going to be something that you can configure. Again, I give Kubernetes, it's not like, I don't think very many of you guys know what Kubernetes is, but that would be software, not really the operating system. But effectively, it's just kind of what you would imagine it is. You have 5 computers, and from those 5 computers, as people want to come in and connect, you'll perfectly, or most ideally, you'll perfectly balance it across all 5 of those computers. So if you have 100 connections in, you'll try to balance them. And this brings us back to kind of the points in basic math I talked about, aka the pigeonhole principle, which is you have a set amount of things and a set amount of, or I guess the set amount of holes and a set amount of pigeons, and you need to fit those pigeons into holes. All right, and how do you do it so they're perfectly spaced out, and you have like perfect amounts going to each one? This is where it all comes back, because if you're doing things like load balancing and you're doing distributed systems, you need to take those connections that people are sending in to access your web server or something, and you need to perfectly balance it across. Now, most of these things are already pre-built for you, and you don't have to do much on your end. But if you want to work on some of the teams that develop this software, then those are going to be good concepts for you to know. Failover. Failover is if a computer fails, what's going to be taking its place. So it would be, let me see if, oh, it is, the article just came up immediately. So basically, like I said, if something fails, something else will take its place. All right, just as you would interpret from the word, if a computer goes down, there will be another computer there to take its place. And a lot of these concepts do work together really nicely. So for example, if you have a distributed system with load balancing, all right, so if you have lots of computers running the exact same thing and you have load balancing going on where all of that data is being sent across or striped across, so it's nice and load balanced. If any of those servers were to just die for some reason, I don't know why, but it just fell over and died, it doesn't matter because you can have and make failover, so anyone that was connected to that server will automatically be failed over and redistributed to working servers. All right, so the big these are big overarching concepts, and they're really applicable if you're doing cloud development, which a lot of you guys will end up doing is cloud development, because that's one of the most common types of like software development where you're making applications and launching them in the cloud. This is where templating, where you're making a template of an operating system, you'll do it all the time in things like Docker or in your virtual machines, distributed, so sharing a load, or having the multiple machines in a lot of different places that are running the same thing. Load balancing, which is going to be balancing the incoming requests across all those machines, and then failover. If a computer dies, there are other computers to take its place. It would be very inconvenient if things like Google, if one of their servers died, all of Google went down, or your email, or whatever. It doesn't happen very often, but when it does, the world is about to explode. I think every time AWS has an outage, which they've had a couple big outages recently, like it always makes the news and people are going crazy. All right, these are in place to help you keep everything up and alive. Some of them are built at the OS level, but a lot of them now, how you'll use them in modern day technology will be applications that you run on top of your operating system. Any questions so far? Can we stop at the hour mark today? Yes, we will stop at the hour mark today. There's a lot from yesterday still to revise and go over, please. Sure, you can go ahead and ask the questions at the hour mark and we can definitely revisit some stuff if you're interested. Okay, so cloud, we talked about cloud previously on networking. That's going to be a server farm, a remote server farm. There's lots of big cloud companies like AWS, Azure, the other one, the cloud, if someone else remembers it, please put it in the chat. I can't remember, I'm blanking on it right now, but these systems or these providers will usually have this stuff not really embedded, because it's not really as relevant, but they'll usually have these applications pre-built and ready for you to go, so you can keep your services in operating systems and whatever you're running alive as much as possible. Information assurance. This is an important term, and this also has pillars. So we learn about CIA triad and the oh no, I'm blanking on it right now. Let me pull it up. This is where is it? CIA triad and information assurance. So yes, we did talk about it. So this is building off of the CIA triad. Again, to go over it, we're only interested in the pillars because I think we saw in the article they were bringing up more stuff than just the pillars. Yeah, like this picture. We're only interested in the 5 pillars of information assurance. This is something that you will be asked on multiple different certifications like Net Plus and Sec Plus. Is this going to be readable? It's going to be your CIA triad plus 2 more items. So we got confidentiality, integrity, availability, authentication, and non-repudiation. All right. Again, these are share some similarities with each other, but have one or two very distinct words for them. So availability, your service is available. If you're making an application, you need it available at all times. It's very, very important. If it's not available, you are losing money, either for yourself if you started your own business or for the company that you work for. And it will not be good for you if you make a boo-boo and things are down for a very, very long time. All right, availability is important. If we look back to these concepts right here, these are all to help you with availability. Load balancing, templating, distributing, and failover will help you keep your systems alive and available at all times. Integrity. Integrity is making sure and guarantees, what it says here, guarantees data associated systems only accessible or modifiable by authorized users. So basically data that's sent and received data that's sent and received, all right, that's modified by the appropriate user is exactly how it's meant to be intended. So if I send you an email, all right, if I send you an email, that email should be exactly how I sent you that email. It should not be changed. That is a very important thing. This is why blockchain technology exists now, and it's gone pretty viral, because the integrity of the system is very bulletproof. All right, it's all about the integrity of the system and keeping logs and tracking everything that happened before it. All right, when users are communicating with you or sending you information, you want to make sure everything is as it is. The integrity is in check. Authentication, ensure users are who they say they are. All right, this is going to be your normal passwords. All right, usernames, biometrics, any security tokens. You want to only have potentially authenticated users accessing your systems. Confidentiality limits access or places restriction on data like personal identifiable information. So there's this concept called PII. PII is going to be personally identifiable information. So this could be things that are very sensitive to someone, like their social security number, their license, or their ID, their medical records. You just don't want those things flying all about. If you are building some type of system that needs to accept these and process them, you need to make sure that they are hidden, all right, that they are appropriately encrypted, they are stored appropriately in a state that if you were hacked, it wouldn't matter to a certain degree, because they should be encrypted on disk. All right, very important to protect your information. This is all about information insurance. So information in general, these are the things that you should be thinking about when you are dealing with information. And then non-repudiation is the very last one, and that is when you send information, you can guarantee when you look at it that that it was you that was the sender and someone else was the receiver. All right, it's undeniable that someone sent something or someone received something. All right, you know for 100% fact that the email that you received from Bob Joe was 100% from Bob Joe. All right, no one else. Someone, could have hacked on his email or something like that. All right, you can't, that's not really repudiational. All right, you need something more, something that will really guarantee that it could have not been anyone else than Bob Joe that sent it to you. All right, that's where, again, these things kind of blend, because that's where you use a mixture of authentication, maybe hardware keys, along with other items to guarantee all of these. They're not just standalone pillars, they have a lot of overlap. Any questions on that? Check the GitHub. All right. I think that's right about the time to take a 3 to 5 minute break. So if you have any questions about what we talked about so far, please ask them in the chat and we'll visit them after the break. And if there are no questions, then we'll go ahead and keep chugging along. I'll see you guys in like 3 to 5 minutes. All right, we are back at it again. So before we get into it, again, we are Rootkit, a non-profit registered here in the US of A. If you like what we're doing here on the stream and you want to help support us, you can go over to this link. We pasted it into the chat. I will paste it again because the links in the description are always messed up. And we have some pillars here that you can help us meet. All donations are being met 1-for-1 for the first 10,000 donations. Also, when you donate, depending on how much you do, you can get yourself particular rewards like our stickers, our awesome collab t-shirt, and this awesome sweater I'm rocking right here with the Rootkit logo in the back. If you have no moolah, that's okay. We're giving away a bunch of free stuff. You can go over to our site, click on blog, and you'll see the week 4 giveaway. On here, you can, click and enter. It's completely free. There's just basic tasks that you need to do in order to get entries. to the giveaway, and that would be stuff like subscribing to our YouTube channel and following our Twitch. All right. I see there are no questions so far. So if you do have questions, please ask them. I can give different concepts to some of these if they're not making quite enough sense. All right. But these are pretty much testing wise going to be terms and then definitions that you will just need to know. Nothing super fancy, nothing super technical. All right. Access control list. So you have files, right, on your computer. How does the computer know who can access what? That is going to be, they're going to utilize access control lists, all right? This isn't just for files on your computer. This goes to things like services that you'll interact with on the internet. You know, who has the ability to upload files to your Instagram? Hopefully it's only yourself, but these access control lists will limit what a user can and cannot do. So there's different ways to tackle this problem, and you can tackle them with multiple different types of access controls, or you can use a singular one. The operating systems that use Windows and Linux both tackle this in different ways. Linux has a very simplistic approach to it, while Microsoft, on the other hand, has a more complicated and robust approach to it. They both work well in exactly how they're intended. There's just different ways to go about it. Because again, your operating system and some technologies that you'll be building, these aren't pre-built-in things. These are things we're used to in Userland when we mess with products in software. But you as a developer, you usually in most cases, you'll have to make this from scratch, all right? So let's take a look at these three different types of control lists. So a discretionary access control is a type of access control by the Trusted Computer Systems Evaluation Criteria as a means of restricting access to objects based on the identity of subjects or groups to which they belong to. The controls of are discretionary in the sense that the subject with a certain access permission is capable of passing that permission, perhaps indirectly, on to any other subject. All right. Any questions in regards to this? I'm trying to think right now of an example. Let's see what they got here in the images. We did stop at the hour mark for our break. Let's see here. Owner of a resource decides how it can be shared. So that's discretionary. It's up to you, the discretion of the owner on how things will be shared. I like this. This is a really good picture, actually. All right. So if you own certain tools, you can choose who can access it. Particularly, the things that you'll be looking for in the computer science space is going to be three things in particular. It's going to be read, write, and execute. So who can read it, who can write or modify it, and then who can then also execute or run the program. All right, those are the typical three traditional permissions that you'll see for each one of these. All right, mandatory access control. Who made these pictures? These are great. Udacity, whoever made these, they did a great job. So mandatory access control. The user works in a company and the company decides how data should be shared. Hospital owns patient records and limits their sharing. All right, any questions in regards to this? Let's see if there's another definition here. Let's see what the... So this might be a good one. Is this a good one? Let's see what the Wikipedia definition says here real quick. So it refers to access control in which the operating system or database constrains the ability of a subject or initiator to access or generally perform some sort of operation on a target object or target. So constrains the ability of a subject or initiator to access. All right. This is going to be at the operating system level. So in this example, it was the hospital level will dictate who can do what. All right. They're telling you who is able to mess with what. In government, this would be, as you can see here, there's plenty of examples. So if you're working in government or in business, they may classify things with certain markings. All right. And this will dictate who has access to what in a big general sense. And then finally, there is role-based. And this is going to be based off your role. So you get certain accesses to certain items based off what type of role you have. So whether you're in sales or a developer or an account manager. This is the most common one that you'll see in most cases in the real world. People really like the role-based one because it makes most sense and it's easily implementable. Is that the right word? Is that even a word? I hope it's a word. I just invented a new word, all right? So everything's based off the role that you have, and that will dictate what type of access you have. So we also have these concepts of a privileged and a non-privileged user. So a privileged user is going to be a user that's authorized to perform some type of functionality, right? They're allowed to do something. And a non-privileged user, of course, is going to be the opposite of that. They are not allowed to do something. They are very restricted, all right, in what they can do. This would be like the difference between someone that's logged into the computer and maybe someone that is a guest onto the computer. Any questions in regards to that? And then we have logging and backups. These are also important overall, and then especially to your information assurance pillars. So logging is very important, and logging is something that happens all the time on everything, and it is extremely important to you as an individual. If you do not log things, you are potentially opening yourself to criminal cases, all right? You need to utilize logging to help in regards to your information assurance pillars. Particularly, it can help you in the non-repudiation and where's my pillars at? Where's the nice, did I pass it? Non-repudiation is the big thing for logging, all right? That you're logging what happens, so when someone does something, you know for a fact they did that thing. You can trace it back, all right? If you are running a big web application or a program that's reporting back to a central server, or maybe you made an operating system, you're in charge of an operating system, maybe you're running an entire IT department, you need to log as much as you can about what the users are doing and what is going on. This is not so you can spy on them like how people commonly think it's for. It's so you can cover your ass, all right? So you can see if things are happening that aren't supposed to be happening. You can track it down. If you've been hacked, you can then track down after the fact. Some people might wonder after things get hacked. For example, we brought up Riot Games several times, so we'll bring them up again. They were recently hacked. How do they know who did it, where it came from? How do they move across the network? This is because logging is happening all the time. Your Windows operating system is logging lots of things that are happening on your computer, and you can access these logs. All right, they're not hidden from you. They're there, they're configurable. You can make it so it logs more, you can make it so it logs less. The point of it is they're there for you to potentially debug and look and figure out certain things. It would not be great for Riot Games or any company that was hacked if they were not logging, because they wouldn't be able to figure anything out after the fact. How are you supposed to patch things or fix things if you don't know how they happened in the first place? So logging is very, very important. And then backups. I think we all know why backups are important. This is going to be for the availability of your data and potentially the integrity of your data. So backups cover several different main areas of concern. One, if a building got blown up that had all of your data in it, your house lit on fire, if you have backups, let's say they were digital backups like to Google Drive or to the cloud, you're okay. You can recover your data later on in an event of failure, all right? Also, backups are useful in the case of, let's say you got exploited. You can back up to a known good before you were exploited, before things went awry. Maybe you wrote a program that is just destroying your whole entire computer for some reason, all right? It happens at times, all right? I'll show you how it happens. I've done it to myself several times. It may be useful for you to have a backup so you can recover things to a state on where everything was stable. So backups are also very, very important. These are built into the operating system. So access control is built into the operating system that you're utilizing. Privileged and non-privileged users are built into the operating system that you're utilizing. Logging and backups are built into most operating systems that you utilize nowadays. So it's important to use these, especially if you're in a professional environment, to again make sure your information assurance is being met, but not only that, that your users are being satisfied. Your users may change depending on your job. Again, if you're working in IT, your users are going to be the people in the company. You need to keep them happy. You need to keep their systems alive. If you're developing software for the world, you know, all those people around the world are going to be your users, all right? So it's important to make sure they are happy at the end of the day. That's how you make more money. Any questions so far? How are you guys feeling so far? Should we continue? Do you guys want to call that a day? Hopefully nothing here is like blowing your mind or too complicated. Me personally, I feel like these things are easier than normal compared to like what we've been covering so far. It's more maybe topics that you're used to, or you've seen the verbiage before, or maybe you've seen the real world equivalent of the verbiage. Just a lot of info. Yeah, it's all just a lot of info. Do you guys want to keep moving forward, or do you guys think you guys are good for today? Drink some of my water. Drinking a lot of coffee. What's the general consensus? Because we are pretty early today, so we could move on through the boot process. Shouldn't take very long to get through it. What is the consensus? Y'all are, you responded there. How are you feeling, Quiet? I'm gonna call you out. I see Decision says that he's down to stop. All right. We can do that. So tomorrow we'll talk about the boot process. The boot process is pretty short and quick to get through. So most likely we will also start beginning in our journey of Windows and talking about a lot of Windows specific things. So everything in this section is only relevant to the Windows operating system. All right. None of this is applicable for the most part to any other operating system besides Windows. And I might pull in Taylor to also help talk about this because he is more of a Windows wizard than I am. All right, sweet. If everyone is happy so far, then we shall call today a day, and I shall, well, before I say that, thank you guys for joining and supporting all the days that you come along and you watch. It's super awesome. But I shall see you guys tomorrow on the next one.